Okay, so let me walk you through the process now for finding or describing the concavity of graphs and also finding points of inflection. And so if we go back to what we were just talking about in the previous video, we know that we need to do a second derivative analysis. We need to know when is the second derivative positive, when is the second derivative negative, and when does the second derivative change sign. So this is actually going to be very much like what we did with the first derivative analysis. Remember where we took the first derivative, we created that first derivative number line and all of that. And so I'm going to call this the second derivative analysis. Now, in a little bit, I'm going to confuse you because I'm going to talk about something called the second derivative test. And that's why I just want to be clear that when we talk about a second derivative analysis, that's where we're just analyzing that second derivative. It's where we're analyzing that second derivative number line, and this is actually a lot like the first derivative analysis that we did in the previous section when we were looking at when were functions increasing and decreasing, and when did we have relative maxes and relative mins. So it's really the exact same type of work, but we have to do it with the second derivative. So for the first example here, if we're going to do this with the second derivative, let's just do some derivatives. And so our first derivative using power rule is going to be negative 4x cubed plus 48x. And then our second derivative is going to be negative 12x squared plus 48. And so just like with the first derivative, we wanted to see when is in the last section, when was the first derivative equal to 0 or undefined. Now we want to say when is the second derivative equal to 0 or undefined. This is a polynomial. We also call that a well-behaved function. So the derivative of that is never going to be undefined, but it is going to be equal to 0. And if we solve this, let's see, we'd have 12x squared equals 48 if I brought the 12x squared to the other side. So x squared equals 4, which implies x equals plus or minus 2. And so if x is equal to plus or minus 2, if that's when my second derivative is equal to 0, then I create a second derivative number line, and I actually label this f double prime, and I put those key values on that second derivative number line. So I emphasized labeling the number line in the last section when we were in class, and now I'm emphasizing once again you want to label this the f double prime number line. And so remember, we're interested in when is f double prime positive or negative, because that's going to tell us when we're concave up or concave down. So we are going to test representative values from these intervals into f double prime. And so if you take something like, I always start with the easy value, like 0 would be the easiest value. And if you took 0 and plugged it into this second derivative, so I'm plugging into this right here, it's going to give me a positive value. And if you took something that's both really big or really small, you could see that when you square that and then multiply by negative 12, I think that's going to be more negative than it is the positive there. So I think it's going to end up looking like this. In which case, remember, this isn't increasing and decreasing for our function now. This is now telling us that our function is concave down on the intervals from negative infinity to negative 2. Also on the f is concave down. I'll just continue that right here. I'll say f is concave down on the interval from 2 to infinity. In addition to that, f is concave up on the interval from negative 2 to 2. And notice these are going to be points of inflection. We are going to have a point of inflection at both negative 2 and at positive 2, because the concavity is in fact changing right there. And so if you wanted to figure out the y value for these x values, you could simply plug them into the function. So I'll just say do f of negative 2 or f of 2. And in WebAssign, they're probably going to have you do that. But right now, just to avoid confusion, I just wanted to emphasize doing our substitutions with this analysis into the second derivative, and keep this simple. If you ever have an x value and you need the corresponding y value, you just go back to the original function. Okay, second example. And what do you know? We've got a log, or a natural log, and so what we should do is probably use properties of logs because we're going to be doing some derivatives. And so I always try to make these a little bit easier to work with. And I could write that to the 1/2 power. So my function, my original function, could be rewritten as 1/2. Let's say this, that's not a negative there. My original function is 1/2 times the natural log of x squared plus 9. So if I want to describe the concavity, and I want to know when I have points of inflection, I have to do this process called the second derivative analysis. And so I take my first derivative, and that's going to be, let's see, that's a constant, so that stays in front, but the derivative of natural log of a quantity is 1 over that quantity, then multiplied by the derivative of that quantity. And, oh yikes, I think we're going to have to do a little bit of quotient rule here. You could see the 2's might cancel, but our first derivative is x over x squared plus 9. So we do in fact have to do quotient rule for our second derivative, because we have two functions of x in between the numerator and denominator. So our second derivative will be the bottom times the derivative of the top minus the top times the derivative of the bottom, and that's going to be all over the bottom squared. So let me just make sure my notation's good there. And the bottom squared is x squared plus 9 squared. Now we would typically be interested in when the second derivative is both 0 and undefined. Oh, you know what? Let's simplify this a little bit. So that's going to be x squared plus 9 minus 2x squared. So I think that's going to be 9 minus x squared. Yeah, that's right. All over x squared plus 9 squared. And like I was saying, we're interested in when is this second derivative both 0 and undefined, and we're going to indicate in our notes, or on the number line here, all of those places. But a second derivative, or any function for that matter, is going to be 0 when the numerator is 0. And if you set that numerator equal to 0, it's going to lead you to x equals plus or minus 3. You know, because you're just saying 9 minus x squared equals 0. So that's going to lead you to plus or minus 3. So those are going to go on my second derivative number line. And then if you set the denominator equal to 0, that would tell you when that second derivative is undefined. But this is never going to be equal to 0, because if you think about it, if you set x squared plus 9 equal to 0, you'd get x squared equals negative 9. That's not going to happen. So take some representative values again, and let's plug them into the second derivative. That's why we label this. So I'm plugging them into this right here. So if I took 0, it's always the one I try to go to first, you'd get a positive 9 divided by, looks like it'd be positive. That's all that really matters. And then if you took something that's bigger than 3, you can see that this would be negative in the numerator, because 9 minus, you know, like 16 or 9 minus 25 or whatever, that's going to be negative divided by a positive. So that's negative. And on this side, given that we always have even exponents, that's going to eventually be negative also. So once again, we can say things like this. We can say that f is concave down. I should say, yeah, I'll just say f is concave down on the intervals negative infinity to negative 3, as well as 3 to infinity. And then f is concave up on the interval from negative 3 to 3. And then we can also say, yeah, it looks like our concavity is in fact changing at those places. And so it looks like, again, we have points of inflection at, I can say, plus or minus 3. And then remember, if you wanted the y values for those, just plug those into the original function. So I'm just going to say f of plus or minus 3. Sometimes you got to watch out, because just because you see these particular, you see the concavity changing at these numbers in the second derivative number line. Sometimes technically they might not be points of inflection. Here they are, but sometimes they might not be if the original function is not defined at those values. And so sometimes that's a little thing that might pop up. But this process is the process you want to use. You typically want to do the second derivative analysis, just like we did it with the first derivative analysis last time. And whenever you're asked that question for concavity or points of inflection, this is exactly what I want you to do.